Dear audience, I'm a third-year physics PhD student at CUNY Graduate Center. Part of my PhD research involves studying 2,6 heterostructures for potential semiconductor disk laser applications. But before going into the details of this presentation, I would like to introduce you to my lab. So I work in Professor Guyon's photonics lab at the CUNY CDI, which is located at the CCNY campus. The field of our research includes semiconductor disk lasers, laser spectroscopy and scanning tunneling microscopy, nanomaterials and nanostructures, nonlinear optics, and optical biomedical imaging. Our contact information is given below in case you would like to reach out to us. Now, given the shortage of time, the content of this presentation is limited. More information is included in the actual poster presentation. This presentation will include our motivation behind studying the 2,6 heterostructures, followed by a discussion on the sample characteristics. I'll report steady state and timeless of photoluminescence, as well as optical gain spectra, and a summary that recaps the content of this presentation. Semiconductor disk lasers, also known as vertical external cavity surface emitting lasers, combines advantages of solid-state lasers such as better beam quality, high power, and optical pumping with that of semiconductor lasers such as complex size, efficiency, and wide spectral coverage. Our design involves separate pump-absorbing barrier layers and emissive quantum layers. There is a scarcity of semiconductor lasers in the 480 and 630 nanometer spectral range, which makes zinc-cadmium selenide and zinc-cadmium-magnesium selenide-based 2,6 heterostructures very promising. The samples that we investigated are MBE-grown 2,6 heterostructures on indium phosphide and indium gallium arsenide substrates. The zinc-cadmium selenide layers, shown in violet, are the pump-absorbing barrier layers with a bandgap of about 2.7 electron volt, whereas the zinc-cadmium selenide layers, shown in yellow, are the quantum wells that emits around 540 nanometer with a bandgap of about 2.1 electron volt. Quantum wells are placed at the antinodes of the standing wave to maximize the gain. The two particular samples that we'll be reporting in this presentation, I'll refer to them as sample A and sample B. The first has 8 quantum wells, and the latter has 16 quantum wells. Diffraction patterns of this sample shows excellent crystalline quality. We performed steady-state photoluminescence on this sample using a CW diode laser emitting at around 400 nanometer. Figure A and B shows steady-state photoluminescence with varying pump power for sample A and B. Both spectra peaks around 565 nanometer. I've included the experimental scheme for the timeless of photoluminescence in the actual poster presentation. For the timeless of photoluminescence, we pump our sample using the second harmonic of a titanium sapphire laser, a blue beam, and the photoluminescence is captured using a straight camera. The straight camera gives us straight images of the photoluminescence, which can be analyzed into a spectra and a temporal profile. The timeless of photoluminescence for sample A shows spontaneous emission at 566 nanometer at low pump power. But as the pump power increased, we observe a spectral shift toward the longer wavelength, and a stimulated emission shows up at about 578 nanometer. And we also observed spectral narrowing as we move from spontaneous to stimulated emission with increasing pump power. Now, the temporal profile of the spontaneous emission shows a lifetime of about 1.4 nanosecond, whereas the temporal profile of the stimulated emission shows a lifetime of about 100 picosecond. So we also observed shortening of lifetime of the spectra as the pump power increased, as we transition from spontaneous to stimulated emission. Similar behavior is observed for sample B. We observed a spectral shift toward the longer wavelength and a spectral narrowing as we increase the pump power. whereas with the lifetime of the spectra shortens as we transition from spontaneous to stimulated emission. We perform the gain measurement using a pump probe scheme. Basically, a pump beam excites a region of the sample. Once the upper level is sufficiently populated due to pumping, a probe beam going through the same region can be amplified due to optical gain. As a result, we can measure the probe intensity while the pump is turned on and the probe intensity while the pump is turned off. And by comparing the two spectra, we can estimate the gain coefficient. Now, this particular experiment was performed in a transmission geometry. As a result, it is important to remove the indium phosphide and the indium gallium arsenide substrate layer using selective chemical etching. More on the selective chemical etching is included in the actual poster presentation. The optical gain spectra that we obtained for sample A, shown in red, peaks around 572 nanometer, which coincides with the stimulated emission peak for the sample, which is also around 572 nanometer. The gain coefficient for sample A was estimated to be 2400 inverse centimeters. The gain spectra for sample B, on the other hand, shows similar results. Again, the gain spectra shown in red peaks around 576 nanometer, which coincides with the stimulated emission. And the gain coefficient was estimated to be about 13,000 inverse centimeter for sample B. To summarize the content of this presentation, highly luminescence 2,6 zinc-cadmium selenide and zinc-cadmium-magnesium selenide based heterostructures were grown using molecular beam epitaxy method for potential semiconductor disk laser applications. We have shown that the heterostructures emit around 540 and 580 nanometer spectral range with a spontaneous emission lifetime of about 1 nanosecond. With high pump power, spectral narrowing and lifetime shortening is observed, which is indicative of stimulated emission. The stimulated emission has a lifetime of about 100 picosecond. We also observed optical gain. The gain spectra overlaps with the stimulated emission. Now that we have observed stimulated emission and gain, we can conclude that zinc-cadmium selenide and zinc-cadmium-magnesium selenide based heterostructures are indeed promising for the development of SDLs in the green-orange spectral range. With that, I would like to acknowledge the contribution of Dr. Jennifer Hess, Professor Dr. Isel, Dr. Will Kirby, Vasilius, and Candice. Thank you. Thanks to NSF Press for supporting our program, and thank you to the audience.